Okay, uniformly distributed random variable. So it has probability density function equal to 1 over b minus a, where b is the upper bound and a is the lower bound. If you look at the cumulative distribution function, that is going to be in this form. Remember, the expectation of x when x is uniform, continuous uniform. Remember, uniform distribution has also a discrete version. So here we are talking about continuous uniform. We don't have actually to get the expectation of x. There is a shortcut formula. I mean, whenever you need it, you have to know that expectation of x, if x is uniform, continuous uniform, is going to be equal to this formula, right? So this is the expectation. Regarding the variance, variance is going to be equal to b minus a squared divided by 12. You can derive it. Yes, you can just use this probability density function and derive the variance and expectation, but no need to do that because there is an easy shortcut formula for that. Okay, so you can try it at home. I don't want to waste time on that. And the notation that we use for uniform distribution is this. We say x is distributed uniformly within A and P. Okay, so if you have A equal to 0 and B equal to 1, the resulting distribution is oftenly called as a standard uniform distribution. Okay, when you have a unit square, then we call it a uniform, standard uniform distribution. I hope it is clear. Please stop me if you have any questions. We can answer your questions. Now let's move to Bernoulli distribution. Bernoulli distribution, this is this is an experiment related to the experiment, Bernoulli experiment, which is random, obviously, and it has binary outcomes. And in Bernoulli trials, Bernoulli experiments, we call one of the outcomes as success and the other one as failure. And it is somehow completely arbitrary. What you are defining as success might be defined as failure in, by me. A nice example, easy example of Bernoulli trials is flipping a coin. Okay, coin flip. It has binary outcomes. Either you have tail or head. Okay, and they are actually, if you keep repeating Bernoulli trials, the outcomes are going to be independent, right? So because the first trial's outcome is not affecting the probability of the probability mass of the second, trial, second experiment, we say that these two experiments, they are actually independent. So remember, Bernoulli trials, Bernoulli experiments, they're random experiments which have binary outcomes, one of which is success and the other one is failure, and they are independent. Okay, if you keep repeating the Bernoulli experiments, they should be independent of each other. The probability mass function of x, if it's Bernoulli distributed, is going to be written in this way. So probability of success, this lowercase p stands for probability of success, to power the number of successes, actually to power whether you got success or failure, the value of x, and 1 minus the p. This is the probability of failure. Yes, if p is success probability, it means 1 minus p should be the probability of failure, and to power 1 minus x, right? Great. Now the expectation of x is p and its variance is p times 1 minus p. This is very easy. You can derive it. Okay, why not to derive it now? Let's do it. Okay. So we say expectation of the expectation of x is equal to question mark given x is Bernoulli. Okay, with some probability of success p. This is how we denote it usually. X is distributed Bernoulli, where probability of success equals to p. Now we can find the expectation using this generic formula. We know that expectation of a discrete random variable x is actually equal to sum over the outcomes, the values of the random variable x. You see, I use lowercase x. So x times probability that random variable x equals to x. This is the generic formula. And because of that, so what is the first value that x can take? That is 0, right? So we can say 0 times, what is the probability of 0? It's equal to 1 minus p, right? Plus, what is the next value? Next possible value of the Bernoulli experiment, Bernoulli distributed random variable, is actually 1. What is the probability of 1? That is equal to p. So when you find the expectation, that exactly gets equal to p. Okay, that is the derivation. So whenever you have Bernoulli distribution, you don't really need to do this calculation. Just keep in mind that the expectation is always equal to the probability of success. Now let's look at the variance. The variance of x. We know that there is a generic formula again, saying that the variance of the discrete random variable x is equal to x minus the expectation of that x. You see, I use like uppercase and lowercase letters. Be careful with them because x, capital X, that stands for the random variable. So we kind of square this times the probability that random variable x takes a particular value x. Okay, because of this fact, the variance of x, which is Bernoulli, maybe I should say, the variance of x, which is Bernoulli, is going to be equal to, so the first value is 0, 0 minus the expectation of x is p square times the probability of 0 is 1 minus p plus the next value is 1 minus p squared times the probability of 1 is equal to p. So if you factor it out, what you're going to receive is, so p squared minus p cubed plus p minus p cubed. All right, let me see whether I did something wrong here. So you got 0, 0 minus p squared. Okay, and 1 minus p squared is the next value times p. Okay, and this should give you what? It should give you, so you get p squared here times, and here you get, should receive, just a minute, made some mistake here. Let me rewrite it. So the first value is 0. 0 minus the expectation of x is going to give you p squared times 1 minus p. Yes, then plus p times 1 minus p squared. I forgot the square thing here. That is the reason. Okay. So here, what you're going to receive is you're going to receive This gives you p squared minus p cubed plus p times 1 minus 2p plus p squared, and that is going to be equal to p squared minus p cubed plus p minus 2p squared plus p cubed, and these p cubes cancel each other out, and in the end you should receive p times, so if I take this p out, it's going to give me p plus 1 minus 2 p, right? And in the end it should give me p times 1 minus p. Okay, this is how it works. So keep in mind that when you have Bernoulli distribution, its expectation is equal to p all the time. Maybe I have to use a rectangle here, and its variance is equal to p times 1 minus p. Okay, so let's move on. What is next? Binomial distribution. So when you have a sequence of Bernoulli distributions, you know, if you have several independent and identical Bernoulli experiments repeated, and you are interested in the number of successes in a given number of trials, Bernoulli trials, that is going to be, that random variable is going to be binomially distributed. Okay, this is a distribution of that. I think you covered all these things in the first part of the sequence, so I don't want to spend too much time on that. So the moment generating function is going to be something like this. Okay, and remember that the expectation, so you can derive it, but no need to do that. So the expectation of the binomial random variable is n times p, and its variance is going to be equal to n times p times 1 minus p. Okay, remember 1 minus p stands for the probability of failure, p stands for probability of success, and it's really up to you to define a particular outcome as your success and another one as your failure. For example, in coin flip, I can define heads as my success. For example, somebody else can define tails as his or her success. It's kind of completely arbitrary. Now let's solve one example. You have a basketball player which has a story of making 80% of the foul shots taken during games. What is the probability that he will miss 3 of the next 5 foul shots he takes? Okay, so his success rate is equal to 80%, right? This is going to be based on this. So we are searching for probability that 3 of the 5 shots will be missed. Probability of success, let's define success as making the full shot. This is equal to 80%. So the probability of success is equal to 80%. But we are interested in 3 failures out of 5 trials. So you can say that this is actually a combination 5 of 2, because if you don't make, you know, 3 full shots, it means that you just make only 2 of them. So 2 of them are successful, 3 of them are not successful. So you can find this probability. Maybe I should write it in this way. I should say probability that you will get 2 successes given the number of trials is equal to 5, is actually a combination. So it's going to be 5 factorial divided by 5 minus 2 factorial times 2 factorial times probability of success is 0.8 to power the number of successes is 2 times probability of failure is going to be 0.2 to power 3, and that is the answer. Okay. So what else? So that is example 2. No, example 1. Yeah, the major assumption, the key assumption here, remember, the key assumption here is that the trials are independent. Okay, independent identity. Probability of making the shot is not changing. Okay, now let's move to example 2. We have probability mass, so we have to find probability mass function of x given you are tossing coins 7 times. Okay, this is going to be a bit, burdensome to write down everything, but anyway, so you have 7 trials and probability of success is 0.5 because you have unbiased coin. Okay, remember, you have an unbiased coin, so it's going to be equal to, so this is example 2 is here, the other one example 1. Now probability that x equals to a particular value of x is going to be found by this function. So combination, so in total you have 7 trials, 7 out of 0, 0.5 to power 0, 0.5 to power 7 if x equals to 7. Yes, you are flipping the coin 7 times. So then you're going to have probability that you're going to receive 1 success is combination 1 out of 7, 0.5 to power 1 number of successes times 0.5 to power 6, right? So if you write down, you will always receive 0.5 to power 7 all the time, right? So you can skip that part. Oops, here x is 0 actually, not 7, it's 0, it's 1. And then you can say that the probability of 2 successes is going to be 0.5 to power 7 times this combination if x is equal to 2. Then combination 3 out of 7, 0.5 to power 7 if x is equal to 3. Now you go this sequence up to 7 success and 7 trials. And that is all. Okay, I hope you got it. If you have questions, you can ask. So the probability mass function is going to look like this. If x is 0, it means that you have 0 success. So this is going to be your formula. And then for 1 success, it's going to be like this. And you write it down for all the cases. Okay. So now you have to find the moment generating function. Moment generating function of x. Mean and variance of x is easy to find. Use these formulas. So look, we have moment generating function of binomial distribution. You just plug 0.5 here. Okay, if you want to write it for this particular case where n is equal to 7, so it's going to be equal to, so this is a part. In b part, you're going to receive so moment generating function of x is going to be equal to p plus 1 minus p times e to power t to power 7. I guess, let me check it. Yeah, actually it is the opposite. 1 minus p is alone. It should be vice versa. So this is going to be your moment generating function. And the expectation of this x is going to be equal to n times p. P is probability of success. So we got 7 trials and the probability of success is 0.5. Therefore, you get 3.5. And the variance of x is going to be equal to, we have already found that this is equal to n times p times 1 minus p, which is equal to 7 times 0.5 to the power 2. Okay? That is the answer to the third question. Okay. What else? Sometimes you are interested in the number of failures before the R success comes out. So here, the last one, you're supposing that the last one in the sequence is success. Okay. In that case, you use the so-called negative binomial distribution. It's given in this. Its PDF probability mass function is given by this. And then we have Poisson distribution. I'm sure that you covered it. Did you cover Poisson distribution in the first part of this sequence in statistics 1? In math stat 1, did you cover Poisson distribution or not? Okay, then Poisson distribution is, you see, sometimes some events, they are occurring, you know, at a fixed intensity, at a fixed rate, or a given period of time. For example, let me give you one example. The average number of messages I receive in this chat room, yes, in the chat box here in Blackboard is 2 messages per minute, for example. Okay, so you see the event is happening at a fixed intensity, at a fixed rate. Okay, at a fixed average rate. I'm talking about a fixed average rate or fixed average intensity. Or you can say that you are, you know, okay. So suppose that in hospital, in a given hospital, in a given hour, actually, on average, a given hospital receives 2 patients per hour. Okay, this is the average fixed rate, intensity rate. In these kind of cases, when events happen in a fixed average rate over a given period of time, we are using the so-called Poisson distribution. It has an important parameter m, or sometimes this is denoted by lambda. So we say the distribution is, the probability mass function is lambda to the power x e to the power minus lambda divided by x factorial. Sometimes instead of mu we have lambda. Instead of m we have lambda. In some textbooks you can see this notation. Moment generating function of Poisson distribution is given by this. Okay, now let's solve one example about that. So you remember, yeah, that is really a key thing. You're going to be using it. Okay, the Poisson distribution, it has mean and variance equal to the intensity parameter, m or lambda, depends how you denote it. And remember that when you have large enough sample size, you can use Poisson distribution to approximate the binomial distribution. That is also possible. What you are doing is basically you are replacing the intensity parameter, the rate parameter m, with n times p, the probability of success. And then you are using Poisson distribution to approximate the binomial distribution. This is possible. Now let's solve one example. You have telephone calls to some number, and that is made according to a Poisson process with average rate 2 calls per minute. So a telephone is receiving on average 2 calls per minute. Find a probability that at least 1 call is made in a given minute. So it's going to be very easy. So you say probability that you know, x is equal to you see, here we have to use a trick here. At least one call is made in a given minute. It is the complement. We are going to use the rule of complements. It's the complement of having 0 call in a given minute, isn't it? So therefore, we're going to use that complementation rule. Maybe I should start a new page. So basically, we have M, the intensity parameter, equal to 2 calls per minute, I guess. Yes, let me check it again. So you have 2 calls per minute, and it's going to be Poisson distribution. So we are interested in probability that x is equal to x is greater than or equal to 1, okay, which is exactly equal to 1 minus probability that x is exactly equal to 0. Remember, Poisson distribution, it has support which is non-negative, okay, it cannot take negative values, but it's unbounded from right side, so it can go up to infinity, positive infinity, okay, it's always non-negative. It has non-negative support, remember that. So this is now is going to be easy. 1 minus, to find this probability here, this is nothing but mu parameter, which is 2 times, so you write 2 to power x, x is 0, e to power minus 2 divided by 0 factorial, which is 1, right? So this is going to be equal to 1 minus e to power minus 2. And that is the probability of receiving at least 1 call in a given minute, okay? That's all. And we know that the expectation of x here, the expectation of this random variable x is equal to its variance, and that is going to be equal to the intensity parameter, m, or lambda. Okay, you have univariate normal distribution. That is really important distribution, but I don't want to spend too much time on these things. I'm sure that you know these things. Okay, so here we have normal distribution. It has, when normal distribution has mean 0, variance 1, we call such a normal distribution as standard normal distribution, and it has this kind of, probability density function. Okay, this is the probability density function for normal distribution. Then what else? And moment generated function is this. Yeah, so you can use the moment generated function to verify that this random variable z has mean 0 and variance 1. You just take the, this is example 4. Example 4. So basically, the moment generating function is equal to e to power 1 over 2 t squared, right? E to power, yes, t squared. So if you want to find the expectation, we know that the expectation of x, actually here we are talking about the random variable z, not x. So let me use z notation here. So the expectation of z is actually the derivative of the moment generating function with respect to t, and then you set t equal to 0. So now if you do that, the derivative with respect to t is going to be equal to what? It's going to be equal to, I guess, 2 times t, e to power 0.5 to power t squared, and then set t equal to 0. That is going to give you an exact 0, right? So, and then to find the variance of z, you have to take the second derivative. I don't want to spend time on this, so you take the second derivative of this function. So because here you have to use the product rule, right? Product rule of derivatives, and then I don't want to spend time on that. I hope you know that. So You just take the second derivative with respect to t, and then set t to 0. This is going to give you the expectation of x squared, and then, you know, in this particular case, these two things are going to be equal to each other. So this is equal to expectation of z squared. In this particular case, because we have 0 mean, the expectation of z squared is exactly equal to the variance of z. So you can find that. And you're going to receive 1 in the end. Okay. What else do we have here? Yeah, so here, remember that normal distribution has two important parameters. One of them is mean, and the second is variance or standard deviation. So if you have these two parameters, mean and variance, okay, if you have these two parameters, then the behavior of that random variable, the whole PDF is completely defined. Okay, these are two important parameters. So what happens if you have, you know, different mean and different variance? What is the general PDF for general normal distribution? So it turns out that you can use the transformation trick to get to this probability density function. This is for general normal distribution. Obviously, if you set mu equal to 0 and sigma to 1, you're going to receive the standard normal distributions PDF. And the moment generated function for general normal distribution is this, very close to what you got for standard normal. Okay, remember, standard normal is normal distribution with mean 0 and with variance 1. Okay. Okay, we have example 5. You have scores of TOEFL test, and they are assumed to be normally distributed with mean 500 and with variance equal to 100. Now, you want to find the proportion of all scores that are smaller than 510. Okay. This is going to be equal to, this is example 5. Let me start a new page. So this is example 5. So yeah, supposing that x is normal, mean is 500, and the variance is 100. So now you want to find a probability that when the variable x is less than or equal to 510, that is going to be equal to, you can apply the standardization technique. So this is the same thing as having standard normal variable being less than or equal to 510 minus the mu divided by the standard deviation, which is 10. So that is going to be the same thing as probability that z is less than or equal to 1. And that is, I guess, I remember that was equal to approximately 84%. This is what I remember, but check it from the table. I'm lazy to do that right now. Okay, so we have solved this. You're just using the standardization technique. You see, you bring the problem of finding probability for general normal distribution to the probability under the standard normal distribution, and then you check the z-table where all probabilities are kind of tabulated. Now, example 6, you have to find a probability that a draw exists 3 standard deviations. Okay, that is obviously going to be equal to 0. It's easy. So suppose you are interested in probability that random variable x is actually exceeding mu plus 3 sigma. You can standardize x by applying this z transformation. So if you apply z transformation, instead of x, you get z. And then if you apply it to the right side, you're going to receive mu plus 3 sigma minus mu divided by sigma, which gives you sigma. So it's going to be equal to, actually not sigma, but 3. So this is going to be the same probability as probability of z being greater than or equal to 3, which is approximately 0. You can check that. It's going to be approximately 0. Okay, you basically apply the transformation z transformation, you get instead of x, you get random variable z, and if you transform the right side, the boundary, and then you get probability that z is greater than 3, which is approximately 0. You can check the z table and you will see that it's approximately 0. Okay. Okay, example 7. So we have a plug beside an elevator in some building, and it tells capacity 4 people and 320 kilograms. Suppose the weights of people entering the elevator are independent. That is the crucial assumption here we make. Maybe I have to use the red color. Independent and normal, and the distributions, they have, all of them, they have identic mean and identic standard deviation. So if there are 4 people in the elevator, what is the probability that the weight limit is exceeded? So you can say that, remember, linear transformation, maybe I have to use a rule. Linear transformation or combination, actually, I should say linear combination. Normally distributed variables is normal. Okay, here we have in example 7, we have 4 people and 300 kilograms. That is kind of the upper bound. And suppose 4 people entering the elevator. What is the probability that the weight limit is exceeded? So I have 4 random variables. This is the first person's weight. X1 is first person's weight. X2 is the second person's weight. X3 is the random variable for the third person's weight, plus the fourth person's weight. All of them are, we know that this is the total weight. Let me call it T. This is the total. And obviously this T is random variable itself. So I know that Xi is actually normal, mean is 75, and variance standard deviation is 15. So it means that the variance is actually equal to 15 squared. So usually we write mean and variance. So mean is given first, and second we write the variance. So for all I equal to 1 up to 4, right? If that is the case, then we can get the distribution of T. Because of independence, remember, the expectation of T is going to be equal to 4 times, because you have identical distribution, identical mean for all these random variables, you're going to receive 4 times 75, which is equal to 4 times 7, it's going to be 300, right? So the new variable T is normal, and it will have the mean equal to 300 kgs. Now let's find the variance of T. Variance of T, because of independence assumption, it's going to be equal to variance of x1 plus variance of x2 plus variance of x3 plus variance of x4, which is, you see, all x's, they have the same variance equal to 15 to power 2, 15 squared, right? So therefore, because of independence assumption, you don't have, because of independence assumption, you can write it in this way. Otherwise, you have to take into account the covariances. So here we're going to receive 4 times 15 squared. That is your variance. So the new, let me use this. So this is the expectation of the new variable T. This is the variance. So the new variable T is actually normal, because I know that linear combination of normal variables is still normal. So T is going to be normally distributed with mean equal to 300 and with variance equal to 4 times 15 squared. Okay. Great. Now what I have to do is I have to find a probability that T is actually exceeding 320 kgs. Okay. And now I'm going to apply the Z transformation. I can say that if I apply Z transformation, T is going to become Z. And if I apply the transformation to the upper bound, I take the value minus its mean, the mean of T, which is 300, and divide by the standard deviation, which is square root of the variance, 4 times 15 squared. And that is going to give me probability that Z is actually exceeding 20 over, so 4 times 15 squared is going to give you 2 times 15, which is just 30, right? It's going to be equal to 30. And that is going to be equal to probability that Z is greater than or equal to 2 over 3. And then you can search for Z table and get this probability. I'm lazy to show it to you because I'm sure that you got it in the first part of the course. So now we have some, okay, example 8, you have two random variables. They're they are not identical in the sense that they have, you see, they are both normal, but the first guy's x1's mean is 6, x2's mean is 7, so they are not identical, but they are independent, meaning that x1 is not affecting x2, right? We have to find the probability that x1 exceeds x2. Okay, so this is example 8. Okay, so x1 is normal with 6 and 1. x2 is also normal with 7 and 1. Now we are interested in probability that x2 is exceeding x1. Okay, so what we can do is we can say that we can take x1 to the left side, yeah, and write it as probability that x1 minus x2 is, oops, here I made a mistake. This is actually about, we are searching for probability that x1 is greater than x2. So this is the same thing as saying that x1 minus x2 is greater than or equal to 0. But to evaluate this probability, we have to find the distribution of x1 minus x2. Let's call it y. Yes, y is equal to x1 minus x2. So this is probability that y is greater than or equal to 0. Now let's get the distribution of y, because we know that the linear combination of two normals here is going to be normal. So x1 is normal, x2 is also normal. So their difference, which is the linear combination of the two, should also be linear. Should also be normal. I can say that y, which is equal to x1 minus x2, it's going to be normal. I'm sure of that. But now let's find the mean and find the variance. So these two guys are question marks. So the expectation of x1 minus x2 is going to be equal to, due to the linearity of expectation, which is equal to 6 minus 7, which is minus 1. So this guy is going to be minus 1. So what about the variance of x1 minus x2? Given independence, this is going to be equal to variance of x1 plus, remember, not minus, plus variance of x2. And that is going to give you 2, right? So this guy is actually equal to, let me use another color here. This is minus 1, and this is going to be 2. So therefore, you can say that probability that y is, so in the end, you can say that probability that y is greater than or equal to 0 is actually equal to probability. I apply z transformation of y, I get z variable greater than or equal to 0 minus minus 1, which gives me positive 1, divided by square root of 2. Okay, that is going to give you probability that z exceeds 1 over square root of Okay, and then the rest is actually you have to look at Z table. The rest is going to be easy. Okay. What else here? Okay, we have distributions related to univariate normal distribution. Yeah, so maybe I stop at this point because I don't want to talk too much about distributions. I think you got tired. Temur, I'm sorry. I'm extremely sorry. I didn't see your question here. Are you around now? Yeah, x means actually exponentiate, like e to power. Yeah, when you write, e to power 5, this is the same thing as you can write it as x5. You see, when you are exponentiating things, sometimes, it's difficult to read it. So therefore, sometimes it's easier for us. It's an alternative notation, that's all. Let's put it in this way. E to power, yeah, Euler's number to power something. Okay, cool. So let me stop at this point. If you have any questions, you're more than welcome to ask. If not, then I'll stop at this point. I don't want to overload you. And please remember that this week we are going to have a deadline for homework 5. Okay. And by the way, this is your responsibility to submit the homework using the Blackboard. We are accepting submissions only via Blackboard system, and late submissions are not accepted. Please submit them in timely manner. Okay. Yes, Timur, please. You're welcome. Okay, let me try to clarify. Okay. Homework 4, question 3. Can you see my screen, Timur? Now let's look at this. Okay. So what is the problem here? Yeah, you have two random variables, y, which is okay, x, which is lifetime, y, which is brightness of a light bulb, and they are continuous. Okay, and their joint probability density function is this. Great, and both of them are positive. Obviously, lifetime should be positive, right? So, what is the problem here? What don't you understand here? So what is the independence? What is the condition for independence? When you say independent, you can use this. You say that. So if x given y, so if probability of x given y, or maybe I should say PDF, is the same thing as PDF of x, then independence. Okay. So what you have to do here, Timur, is first you have to take the like what you can do here. You have to get the conditional distribution of x given y, for example, or conditional distribution of y given x, and check whether this equality holds or not. Okay. You can get a conditional distribution. I hope you know how to do that. If you check the lecture, you can find an example where we're dealing with the conditional density. Lambdas, there are some parameters, some positive parameters. Probably we should have told that there are some positive parameters, yes. What you can do is, I guess it's Okay. Now I get what you mean. Yes. Hmm. Okay. So suppose there are some positive parameters, some positive. Yes, there are some positive constants. Exactly. Here you have some exponential distribution, joint exponential distribution. This is called exponential distribution. We have not covered it yet, but I think you got it in the first one. It's kind of joint exponential. I guess you should receive, probably you're gonna receive independence here. I don't know. I'm not sure. Yeah, I'm not sure what you're gonna receive, but just treat them as positive constants. In the end, if you cannot pin them down, you can say that, okay, in these values of lambda one, Timur, you can say in these values of lambda one, these x and y, they are going to be independent. I don't know whether you can pin them down or not. If you cannot pin them down, you just say that if lambda is, for example, positive, I mean greater than 5, then there will be independence. Otherwise, not. For example, I don't know. I have to solve it. Okay, but the general strategy is just to find the conditional density and check whether it is equal to unconditional density or not. Okay. Other questions, problems? Okay, guys. Then I'll stop at this point and take care. Have a good day.